Okay, very good. So let's start. Okay, so now let me recall what we did doing last lecture. So we were taking the second point of view on moduli spaces and Riemann surfaces in general. This was the Riemannian metric aspect of Riemann surface theory. So basically, we wanted to see this correspondence, Riemannian metrics on sigma, how to get complex structure on sigma and more or less back and forth. It's not quite back and forth. We'll see that basically Riemannian metrics on sigma up to conformal equivalence. We'll see that up to conformal. Okay, but for this direction, actually, we don't have to go to conformal classes. I mean, for this direction, I can start with a Riemannian metric here, and then I give you a complex structure. So let me show you how. So Riemannian metric. So basically, sigma is oriented smooth surface with metric G. So let me show you how to define a complex structure on sigma. I mean, this is left to right, right? Complex structures. Let's see how we can do it. I mean, for this direction, we need a deep theorem that is a result of Gauss, which is this is called local uniformization theorem. So this is Gauss local uniformization theorem. What does it say? It says that for any point P on sigma, there exists local coordinate chart mu and phi around P phi from U, which is an open subset of sigma, to phi of U, which is an open subset of C, such that in this coordinate, the metric has a very natural, very beautiful shape. Because the metric in general is G mu nu, dx mu, dx nu. It has 4 smooth coefficients, but it has only one parameter in this coordinates, which is e to the h, dx squared plus dy squared. You can always arrange so that in that coordinate, the metric looks like this. Right? I mean, now if the coordinate that Gauss gives you happens to be not related to the orientation of the surface, that's okay. You can change the coordinate. The metric is still going to be in this form, and it's going to be an oriented coordinate chart. So the upshot is that locally, I can always choose an oriented coordinate chart in which the metric is of this form. Okay? And I claim that these charts mu I phi I actually defines a complex structure for me. Is a complex structure. sigma. So by this, I mean that if we go to transition, study the transition functions of these charts, they're going to be holomorphic maps. Okay? So i.e., basically by J inverse composed with phi I from phi J of Ui intersection Uj to phi I of Ui intersection Uj are holomorphic. Well, I mean, what happens is that these maps are conformal because of these conditions that we have. They are in this form in local coordinates, so preserve the metric. So in fact, proof of this, since phi J inverse composed with phi I is, it has two properties. It's orientation preserving and it's conformal both. It is conformal and orientation preserving. You conclude that actually these are holomorphic because we know that holomorphic is nothing but conformal and orientation preserving. These are the two conditions. Implies that by Ji equals by J inverse is holomorphic. This is the comment that I did yesterday. For all i's. So in fact, any metric on your surface gives you a Riemann surface structure in an unambiguous way. Now, how to go from right to left? From right to left, we'll see that we can only get a conformal class of the metric, not an actual metric. So how to go from complex structures on sigma, how to get a conformal class of metric. I mean, the idea is very simple. It's very similar to this actually. So basically, let ui phi I be these charts which are defined the Riemann surface for you, the morphic chart. Now, you just use these phi i's to pull back the metric on the plane to the metric on your local coordinate system. So let gi be equal to phi I star of this metric g, where g is this Euclidean metric x squared plus 3y squared in C. We have this flat metric on C, right? I just pull it back, I get a metric on UI, right? Because this phi I goes from UI to phi I of UI, which is in C, I just get this metric. So basically it means that if you are in this coordinate chart UI to measure distances on this UI, you just go to the plane, you measure distances there, and that's your distance. I mean, there's a change of coordinate. That's okay. Now, this metric, of course, has a class, conformal class of GI. Okay. Now, if you change if you are on a different coordinate system, if you look at this metric, Gj, which is phi j star of G, because this change of coordinate is polymorphic, the class of Gi is conformal class of Gi is equal to conformal class of Gj on Ui intersection J, because this guy is phi j intercomposed with phi I is a conformal map. And that's all. So the conformal class of the metric is defined. And it doesn't matter that we cannot define the metric exactly, but conformally. So that's the end of all of this thing. So basically, this is the one-to-one correspondence between complex structures on sigma, Riemann surface structures, and conformal classes of metrics on sigma. So I was looking for some object around here that would be like a surface. So if you have a surface in space, any surface, take a donut for example, or pretzel in space. This gets a metric from the ambient space, three-dimensional space, right? It gets a metric. And if you change the surface in space, you get a different metric. So you get a complex structure, and these different complex structures, they are not necessarily equal. So you can take a shape, a surface in three-dimensional space that's deformable, and deform it with the same topology. And as you deform, you are kind of defining a path in the moduli space, because these corresponding Riemann surfaces need not be isomorphic to each other, because different metrics, they don't have to be conformal. So this picture of Riemann surface theory is very, very physical. I mean, you can see it in three-dimensional space also. Okay, so then, so this gives us now a perspective on Teichmuller space. So this gives us alternative definition of Teichmuller space. G. Okay. For this, I need to prove something using uniformization theorem. So the proposition is the following. The proposition is that let sigma be a Riemann surface. Then there exists a unique metric of constant curvature so this constant curvature is equal to -1 if genus of sigma is bigger than or equal to 2, equal to 0 if genus is equal to 1, and is equal to 1 if genus of sigma is equal to 0. Yeah, Riemann surface. Then there exists a unique metric of constant curvature on sigma. So I have to be careful about uniqueness in this case, in the genus 0 case. But certainly in the genus bigger than or equal to 2 case, the metric is going to be unique. So I'm going to. So in fact, we can see this as an alternative form of uniformization theorem. So I can call this uniformization version 2. So let me call it uniformization theorem. To prove. So what we do, we just go to the universal cover of sigma. So we have this covering map from universal cover to sigma. This is the covering map. Right? Okay, now this sigma tilde is either H, upper half plane, right? Or complex plane, or CP1, right? And we know that sigma is equal to sigma tilde divided by some group gamma. This group is a discrete subgroup of the automorphism groups of one of these things. Okay. Now, so sigma tilde has a metric of constant curvature in each case. I mean, this case has a metric of constant curvature equal to -1. If sigma tilde is C, has a metric of constant curvature is equal to 0. And if it's CP1, it has a metric of constant curvature 1. Okay, so this is the covering map by this discrete group action. So you can induce a metric here to this, because this is locally an diffeomorphism between open sets here and open sets here. So you can use this metric to define a metric here, and this curvature of this metric is going to be curvature of this. So this is the construction. So this is a version of uniformization theorem that sometimes people prove this. I mean, you can also express it in a different form. Is that if you have any metric, so let me give you yet another version. If it's quite like this, the version is that. I mean, I didn't discuss uniqueness yet, so I will discuss uniqueness later on. So this is the alternative formulation. If sigma and G is an oriented Riemannian manifold, then there is a smooth function H on sigma. No, to R smooth such that e to the H G is a constant curvature metric. Constant curvature. So in other words, you can always conformally perturb your metric such that it's a constant curvature metric. I mean, if you think about what we did over there and these correspondences, and this is covered for this. Okay. So yeah, you can call it. This is also a uniformization theorem. It's a version of uniformization theorem in this form. So, right, right. But now about uniqueness. So for uniqueness, so I can give a very nice exercise to if you do that, you learn a lot of differential geometry, properties of Laplacians, and then also you'll understand this issue. So let me give you the exercise. So the exercise is this. Let sigma be a closed. So, I mean, here closeness is important. So let sigma be a closed yeah, smooth surface oriented with surface. Let G1, G2 be metrics with constant curvature -1. Constant curvature -1. So K, so the curvature of G1 is equal to curvature of G2 is constantly equal to -1. So in particular, genus of this guy is bigger than equal to 2. Okay. Then G1 is equal to G2. Oh, oh yeah. Assume that they are no. Assume that they are actually conformally equivalent. Assume G1 is equal to e to the h. I'm sorry, e to the h G2. They're conformally equivalent. Then actually they are equal. Then G1. So this is an important question that is related to this uniqueness here. If you have two metrics that are constant curvature and they are conformally equivalent, then they are actually same. Constant curvature -1. But you need your manifold to be closed. If it is not closed, then it doesn't hold. Right? So that's a very nice thing. So what you need to know is you need to know the relation between curvature of a metric, its relation to curvature of a metric which is conformally equivalent to that. And there's a formula which is called Liouville's formula, which was discovered a long time ago, and you use that formula and then you reduce things to questions about Laplacian, which is not very difficult, but I highly recommend you. So this is the first case for genus beginning to 2. If genus of sigma is 1, we have to assume area of sigma with metric G1 is also equal to area of sigma with metric G. You have the same area. If you assume this area condition But amazingly, this does not hold in the case of a sphere. And this uniqueness fails in the case of the spheres. I mean, this also I want you to look at it because that's kind of very interesting issue. Okay. Before I move to this tau G, Tausch-Muller space, one more remark. I mean, if you have seen this, this is trivial, but I just still I want to tell you why, if you have a constant curvature -1, genus is bigger than or equal to 2. Why, if you have a surface of constant curvature -1, its genus has to be bigger than or equal to 2. And vice versa. I mean, if there is a metric of constant curvature, then that constant number has to be -1. So yeah, okay. Maybe in the audience, I don't. Okay, so the reason is that is something very famous theorem called Gauss-Bonnet theorem. So let me tell you what is Gauss-Bonnet theorem. So Gauss-Bonnet is the following. It just tells you that the Euler characteristic of sigma. So sigma G is closed, oriented, Riemannian. Then goes when it says that Euler characteristic of sigma is equal to 1 over 2 pi integral curvature dA over C. This is the famous theorem that was discovered by Gauss in the local form and then was generalized to the global form for Gauss on a two-dimensional, and then it was generalized to two n-dimensional cases. Okay, so if you just put into this, so you have got 2 minus 2g is equal to 1 over 2 pi. If it is constant, k times area of sigma. So k equal to -1 if and only if g is bigger. From here you get. So the curvature actually controls topology, right? And that's one of the first examples of how curvature controls topology, which is weird because we think metric should be about something else, but it actually controls topology too. And topology also controls metric. It's a perfect connection between them. Okay. Yeah, so now in view of this proposition, we can define this Tausch-Muller space in an alternative way. We can give an alternative definition of Tausch-Muller, which is the following now. So tau G so tau G we can define as the space of all metrics of constant curvature -1. So let's assume genus is given. We can define tau G to be a space of constant curvature, which has to be equal to -1 matrix on sigma, we put all possible constant curvature metrics -1 on sigma and divided by this diff plus 1 sigma. So this was the connected component of identity in diffeomorphism. See, this was the connected, right, component of identity in this topological group this class of sigma, right? Okay, so I should say how G of sigma. I have to fix this sigma as well, because we want to be specific about something very, very concrete. Right? Remember, before we defined it differently, right? We defined it before, we defined it to be, so this compare with the first definition, how G sigma was all complex structures on sigma, right? Divided by this group. Right? We had this definition originally, which is very natural. This kind of strange, but because of these things that we did, the two things are the same. Yeah, so that's it. And here I just say that, okay, so mg is just lg sigma divided by gamma g. But this gamma g is the mapping class group. Gamma g is mapping class group. Which is, of course, this group divided by connected component of identity, right? Which is the plus sigma divided by plus 1. So it just is a group of connected components of this diffeomorphism, because there's many connected components, and you don't divide. Okay. Right. So, okay, so I went a little bit off the tangent here to discuss an alternative description of this Schmuller space and mapping class group. Now, let's go back to what we wanted to cover at this little bit. Okay, so we can now actually, yeah. Okay, now we can the marking on the surface. So surfaces with one marking. I mean, we can define analogs of those objects. So we define tau G1 and then gamma G1 and then MG1. So this is the Schmuller space of surfaces with one marking and mapping class group, which is tau G1 divided by M G1. So for example, this gamma G1 is the diffeomorphisms of is so these are the diffeomorphism that preserve this point P. Everything is for the marked surface. And this is the connected component identity of this group. So obviously this is a subgroup of the class of sigma as we find out. Okay, and now the Zagier theorem wanted to compute this Euler characteristic of this group, gamma 1G, which because of this relation, and because this is kind of contractible, which is essentially Euler characteristic of M1G. This is the Euler characteristic of this one. Because this is contractible, this group is acting, oh, this is terrible. Gamma 1G. Yeah. Okay, so this is a long calculation, and actually it has many deep and interesting ideas. So this, no, I mean, this is the definition. I'm sorry. So this question is, what is this, basically? And in fact, answers the theorem. The theorem is the result that answers this. Gamma 1D is equal to negative B 2G, the Bernoulli number 2G divided by 2G. Right, that's so note that we check this by hand in case G equal to 1. So what we did in that case, we computed this by gamma 1G. In fact, gamma 1G in this case is equal to gamma G as groups, they are the same. Okay, so let me get 1 then. This is equal to 1. And this is the group PSL2, this is the group SL2Z actually. And we computed this Euler characteristic of SL2Z, it came out to be minus 1 over 12. Right? And if you go through this, this is equal to, in fact, the negative B2 over 2, because B2 is 1 over 6. So this is verified, in this case by hand, and but the theorem is true for all genus. So it's I was debating with myself if I should give the proof or not, because first of all, I mean, it's a long proof, it's very, very complicated, it involves a lot of different ideas. So each of them, if I want to open discussing it, it will take a long time. So I will just give a very, very, very brief account of the thing. So let me tell you what I have. I mean, one thing is what it has to do with random matrix. Because I mean, why this is related to random matrix theory at all? Because this seems to be a question of topology and Riemann surface theory, differential geometry, and all this thing. And now all of a sudden, the proof, I mean, the statement, there's nothing about random matrix in the statement. but why the proof can go or will go through, at least one proof, there are other proofs as well, goes through random matrix theory. I mean, this was the first proof that was discovered, by the way. Pardon me. So the first thing is that using a combinatorial model for this for gamma 1G, okay, one relates the let me put it this way. Yeah, one relates Euler characteristic of gamma 1G to polynomial gluings. Right? So let me tell you what I have in mind. So you remember we had, when we were discussing random matrix theory, we had this thing that if you have a 2n polygon, right, or a 2n gon, yeah, for example, 6, but that's okay, or 8, I don't know. What is it? Is it 8? I hope it's not 7. 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's 8. Okay. So we defined let epsilon gn be equal to number of ways you can glue a 2n gon into a Riemann surface of genus G, right? Right. So, yeah, this epsilon gns are important numbers. I mean, if you have a 2n gon, label 2n gon, if you glue them across from these edges, 2 by 2, you always get a Riemann surface of some genus, but the question is in how many ways you're going to get genus G for each G. And this was related to random matrix theory because this was related to question of computing moments, tracial moments, you remember? So the issue was the following. Trace of H2n turns out to be equal to n to the power n plus 1 sum epsilon g n over n to the 2g g bigger than 6. This was the genus expansion in this case, right? Well, I mean, so this is expectation value. So what is this? This quantity trace of H2n expectation value is by definition equal to integral of trace of H2n d mu of h over the n by n matrices, right? Hermitian matrices. Well, of course, d mu of h is equal to, yeah, d mu is 1 over z0 exponential of -1/2 raised of h2 dh. This is the Lebesgue measure on the space of Hermitian and Bayesian matrices, and this is normalized, so is a total mass 1, is a probability measure, and okay. This is what we did first day when we studied random matrix theory. But then, in the same paper, Harazaki proved an expression. So for example, we showed that for 0 epsilon 0, what is my notation? Epsilon 0 n. So this is the number of ways that you get a sphere, genus 0 thing. So this is called planar terms. Number of ways you get a sphere is the Catalan number Cn. That's what we saw. Do you remember the Catalan number? Was it? 1 over n plus 2n. Excellent. Yeah, 1 over n plus 1, 2n choose. Yeah. And as you remember, this also was used as a side way on the side. We use it to prove Wigner's semicircle law and all this, because these are exactly the moments of the semicircle law also. So let me just write it. So this is an aside, but this is crucial observation for semicircle law is that, 1 over. So what is the area of a circle of radius 2 is 2 pi r squared 4 is it 2 pi, right? So it's 1 over 2 pi integral x to n root 4 minus x squared dx from -2 to 2 is also equal to Cn. So this is an elementary calculation from calculus. You can do it as we said. And okay, so but this is an aside. I don't need it now. Okay, so anyhow, this epsilon 0 n is easy to calculate. Not so bad. It's okay. But for higher genus, it's extremely hard to know what these are. But Harazaki computed this. They have an expression for that. And I want to write it here. Remember, I mentioned using theory of orthogonal polynomials. Yeah. So Harazaki prove that, so what is a good way to put this expression? Because there's a polynomial there. Yeah. Yeah. So they proved that actually this moment trace of h to n is Pn n where Pnx. Yeah. is a polynomial that they explicitly calculate in some sense. It's 2n factorial divided by 2 to the n factorial sum in from 0 to n, and choose p, go to the p, and then x times x minus 1 times x minus p divided by p plus 1. So, yeah, I mean, okay, if I put x equal to n here, you see, I just get expressions in powers of n, but here I have expressions in powers of 1 over n. Oh, well, there is n to the power n plus 1. So actually, all powers are positive. There are no negative powers in this expression, right? This is clear. Okay, so there's no problem. Okay, so this is what they proved. Okay, but this is from back then. What it has to do with this Euler characteristic. Then they showed that let mu gn, they introduce another number, mu gn. So this is a number of ways of gluing a surface of genus G without gluing two adjacent edges. So this is a restriction now. Without gluing two adjacent edges. Because I mean, for example, here you can have this kind of gluing here, and this kind of. I mean, you see. Okay, so I have to tell you what they are. I mean, this. Now you're gluing these two adjacent edges. You may get some surface of some genus, but that's not accepted. So you have to delete that from your list. And you get this number, mu gn. And there's another number, lambda gn, which is what we need. So this is an intermediate number, but let lambda gn. Same thing as above. Number of ways of gluing the genus G surface without gluing two adjacent surfaces to two adjacent surfaces. So instead of 1, 1, we just go 2 by 2 now. Without gluing pair of edges. Pair of adjacent edges. To a pair of adjacent. To another such a pair. So yeah, I mean now you don't have to understand anything now at this stage because this is completely. I'm just giving you very sketchy thing without really giving background. I mean, but it's related to the polygon gluing. The question gets related to polygon gluing, and question of polygon gluing and these numbers is related to random matrix theory. And in one case we have that, another case we have that. And finally, then Euler characteristic comes out to be like this. Finally, they prove that this is some what's this big formula? There is a formula for lambda GNs in terms of lambda GNs. Yeah. Sigma sum over n minus 1 to n minus 1 lambda GN. Yeah, divided by 2. So the Euler characteristic that we want to compute eventually gets related to certain types of polygon gluings. Okay, then they use with some more work. Let me put it this way. They use this formula. Okay, first of all, they connect lambda GN to mu GN and mu GN to epsilon GN. This part is not so bad. I mean, it still is ingenious, but it's not terribly difficult, but it is difficult, really. They relate these lambda GNs to mu GNs and mu GNs to epsilon GNs. So there's like a, so this mu is like an intermediate step. And use that relation star to compute, to show that double star, which is this one, is actually minus b into g. This is a very brief sketch of the proof. It goes through several very deep ideas, pieces of mathematics, and it needs some. So it takes time to really go through that. I thought it's not particularly useful for us now to go through the details, so I'll just keep it at that, and then we'll decide what to do next. So for now, I think, yeah. Okay, so I think we can stop now, actually. So we have 1 hour left, but we can just come back next time and spend a little more time next time. So are there any questions? So for the Zoom audience, I'm going to send some schedule for the rest of the term and also maybe scheduling your talks and stuff like that. Thank you, guys. So see you next week.